Welcome back, everybody. I hope you enjoyed your break. I would like to introduce Ricard Borras Navarra, Senior Machine Learning Engineer at Veriff, specializing in pioneering computer vision products. Ricard has transformed into an MLOps specialist, empowering Veriff's data scientists with cutting-edge tooling. In this talk, titled Deploying Computer Vision Models at a Scale DevOps-free, Ricard will delve into how Veriff leverages a blend of classic software engineering techniques and advanced AWS tools to reduce model deployment time from 10 days to just 1 day, alongside slashing inference cost by 75%. Please give a warm welcome to Ricard Borras Navarra.
Thanks for your welcome and congratulations for the pronunciation of my name. Hello, I'm Ricard Borras from Barcelona, Spain. And today I'm going to talk about how we deploy our computer vision models in my company. First, I will introduce what does my company do. My company is called Veriff, and it's an Estonian company which provides an identity verification solution. So basically what we do is we ask for the customers to take a selfie of himself and later a photo of any ID document. We support more than 10,000 different documents from all the world. And later on, we run several checks, several verifications to ensure that the human behind that transaction is a real one. It is used by banks, but loan companies, etc., by all different types of companies that need to verify that the people is a real one. So as you can imagine, we apply machine learning. In this case, we apply not only computer vision, but also tabular data machine learning models. And we run several models. We run models working in the selfie image. For instance, we do face detection. We do face liveness to ensure that the face is real. We estimate the age of the person from the photo. But also for the documents, we do the same. We need to detect the document, to extract the characters inside the document, to classify which type of document it is, to see if the document is fraudulent or not. Maybe it's a photo and it's not valid, etc., etc. So as you can imagine, we do a lot of models, different models running at the same time in production systems. And that need to be in real time, so they need to be fast. So first, I will introduce how we did it before, 1 year ago, and afterwards, I will introduce how was this journey between the previous state solution and the current one. So before, the company was working with microservices, as everyone, let's say it, and microservices running in Kubernetes in the cloud, cloud provided by AWS, where basically we have microservices for all the different tasks in the company. So one type of microservices is this machine learning microservice, which basically contains a model inside and runs in that Kubernetes cluster. The thing is that computer vision models are not easy to run because they require GPU to work fast, and the GPUs are difficult to get and are very expensive compared to other type of instances. So we know that with this solution, where we have a machine learning service running in our Kubernetes, we're paying a lot for our services because we have several a unique model for each service. So to overcome that, we developed a custom solution to share GPUs between services, but it was not really optimal. So if we look inside of what is inside these machine learning services, basically all of them work the same. We have image fetching, which is downloading the image into the memory, run some pre-processing, image normalization, etc. Run the inference part, and later some post-processing, maybe a calibration, etc. If you look deeply, you can see that the pre-processing and post-processing do not need GPU at all, but they are consuming GPU nodes. That's a way of wasting GPU resources. Also, we have just one model for each microservice, and that's a problem because we are not maximizing GPU usage. Also, as we have a model for each service, we cannot share GPU. We cannot run batch processing. That means that we are also not maximizing GPU usage. And if you want to develop a new model or deploy it, you need to develop a new machine learning services. So basically, this has a lot of drawbacks, and the main important ones is that the development time is super high, because this machine learning service, which need quality-grade production code, needs to be developed by the data scientist usually, and he or she doesn't know how to do it, and it takes a lot of time for him or her. And yes, that running that GPUs, because we are not running them efficiently, it's very expensive. And also, as we have these models embedded inside the service, are very difficult to reuse. So I will introduce what we do to overcome this bad situation. And there are two parts of the solution. The first part is Triton models. Triton is, in fact, it's Triton Inference Server. It's a software developed by NVIDIA, which basically takes your model weights, you add some configuration files, and you have a nice API around your model. So it's a no-code solution. And the process of developing is more or less like this. You take your model weights, you take your configuration files, and you build a model repository. That model repository is just an arrangement of files. With that, Triton server can boot and serve that models contained in this model repository, and serve in using an API. It can be HTTP or gRPC. That runs again in a GPU node. No changes here. So the good things about Triton is that it supports a lot of training frameworks. So it supports PyTorch, TensorFlow, XGBoost, etc., and different backends. So you don't need to have your model in ONNX. You can run Python models, just Python plain functions. And you can run tree models, NLP models, etc. So it's really convenient. And also it has nice features for GPU optimization, such as dynamic batching, where the server joins different requests to the same model and runs them in a same batch, maximizing the GPU usage. Also, it supports multiple models and multiple versions of each model. That's interesting because when you're developing a new model, maybe you have a stage where you have two versions of the same model at the same time to allow the consumers to update the version. So it's interesting to have these multi-version features. So the good things about Triton is that it requires no code, so it's fast to develop. As there is a standardization in the APIs, because all the APIs are the same, it allows for easy reusable. The APIs, to make you an idea, is just basically a model name / model version. And with that, you can call any model in the server. You can build inference pipelines, which is interesting. If you remember from the previous slide, we have this pre-processing, this post-processing. You can build all in Triton and make a unique request called all the models in the pipeline. So you can join several models in the same request. It's interesting to maximize the throughput. And again, you can have multiple models, multiple versions. But we still haven't resolved the key question for cost management, which is GPU running. The GPUs are still running in Kubernetes. And that's a problem. So let's see what can we do for that. I will introduce the other part of the solution, which is AWS MME. MME stands for multimodal endpoint. So basically, it's a mini cluster composed of 3 parts, which runs multiple models at the same time. What's inside a MME endpoint? Basically, you have a fleet of instances which run models. That part is easy. But you have a load balancer that sends the request to the proper instance. So if you have, like here, 2 instances, it will send requests for model A version 1 to instance A, and request to version 2 to instance B. And that models will be loaded from a S3 bucket. So in that S3 bucket, you have all the models. You can have thousands of models in that place, models and model versions. And only the needed models are loaded at the same time. How? Load balancer takes care of checking if the model is already loaded in an instance, and in case not, it loads it to the instance that has more space available. The good thing is that you can fit any type of instance that you want in that cluster. So you can have GPU instances, but if your models do not require GPU, you can just use CPU instances. Also, that instances are dynamic, and we will see how this instance can be added or removed from the mix. And one point is that the models, the inputs, the contents of this S3 are Triton models that we have seen before. Okay, in terms of autoscaling, here is a typical consumption pattern from a week in my company. And every horizontal line, it's the number of requests that fit in an instance that we have seen before. So to fulfill the maximum peak of traffic, we have 7 instances. But we see that if we allocate always 7 instances, we are wasting a lot of money. In fact, if we take the integral part of this chart, we will see that more or less we need an average of 3.5 instances. So we can save the 50% of GPU usage. So that's where autoscaling takes into account. By knowing these autoscaling rules, that it's basically a super easy to set up rule that says when the number of requests for a given instance is below a certain number, add another instance or remove an instance, depending on that threshold. So the good thing is that the GPUs are managed by AWS, so you don't need to manage yourself. And these autoscaling rules allows to minimize the GPU, the number of instances that you need. And also, in terms of DevOps, you don't need them because you set up these autoscaling rules one time and you forget, with proper alerting, of course. And the models are really easy to deploy because you just copy them to S3 and that's all. However, the model artifacts that Triton models needs to be built. That could be done by data scientists, but it's something that it's not difficult, but it's error prone. And also, Amazon doesn't give us model metrics, just cluster metrics. So we cannot know how exactly is our model performing if we have several ones at the same time. So how we implemented both things in my company. Basically, this is the architecture, super easy. We have, for the MME part, we have just 2 endpoints, two clusters, one for staging, for development, to try new models, etc., and one for production. That's all. In both of them, we have all the models, all the versions in the company. So we can have, again, hundreds, thousands. And that clusters emit some CloudWatch metrics that we ingest. How we build that artifacts that we have in these buckets? Basically using a monorepo that I will describe now that takes care of building these tar files that are the contents of the MME part. And how we consume the models? Basically, by using a client that we develop that sends a request for any consumer and produces some Prometheus metrics at model level. That's interesting. What kind of metrics that we can have? We can have latency metrics, so we can compare which is the most expensive model in the company, which that version is really faster than the previous one. We can see how popular a model is, or which service is consuming which model, etc. So we have a nice metrics here, and nice alerting also. And taking more details in Git monorepo, this is the tool that data scientists use to build and deploy the models. Basically, they take their model weights and that configuration files in all the models of the company in the same place, in that monorepo. We have some shared tooling that run the unit tests for each model, so we are validating that the models are really valid by booting a server automatically, loading the model, seeing if the model could be loaded, and running some tests on that server in the unit testing part. So you ensure that the model is working as expected. After that model is valid, you can run this conversion of the model, so building data files, packing the Python dependencies, etc. And when everything is correct, you can deploy to staging when you are working in a branch. So immediately, when you commit and push to your branch, you have your model available to run some inferences in staging. And when you're happy with that, you merge into master, and you have your model deployed into production. What does it mean? That by deployment, you just need to merge your pull request. That allows to have our models in the same place and with the same standard quality of code quality, unit tests, etc. And all this run in this continuous integration part. So we have overcome all the drawbacks that we have because the GPUs are managed by AWS, the autoscaling minimize the costs, and the models are really easy to deploy. And we have very nice metrics and the quality control for models before deploying them into production. So just to summarize, we reduced the model deployment time from 10 days to 2 days, and with zero DevOps support. This is really nice for the data scientists that can focus on building new models instead of deploying them. And in terms of costs, we have reduced it more or less 75% in terms of GPU. And also, the DevOps time is not wasted managing that clusters. However, we have some issues, and this is, for instance, the autoscaling part that adds or removes instances to the mix. We see here how the autoscaling works. We see that in this horizontal line, we have the threshold to add or remove instances to the mix. When this happens, some requests take more time than usual, and that means that we have some timeouts. So to use this architecture, you need to have a good retrial mechanisms in order to ensure that the requests that take a lot of time are retried because we have these auto-scaling things, artifacts. So the next steps for us is the integration of that architecture with our model registry. So you can close the circle between experimentation, model registry, and model deployment, just closing the circle. And also taking advantage of the nice tooling from this MME, which is A/B testing, where you can run A/B tests, changing the instance type of AWS. So you can try the new Gravitron instances or whatever, with just a percentage of your traffic, and in case that works, you can convert all the cluster to the new instance type. And that's all from my side. Thanks. Any questions?
Much. You have some questions? Just wait for the microphone. Microphone here, please. In the first row.
Thanks, great talk, really enjoyed it. Could you go back, please, to the slide with the final architecture? Yes, Monorepo and Prometheus, are they cloud services or commercial products or open source? And how are they deployed on AWS?
Prometheus, where we have a server which is deployed in our cluster. So that low part is all deployed in our cluster. So yeah, Prometheus is a server that you can send metrics to them, and it takes care of storing and logging them. For Monorepo, it's just a bunch of Circle CI, in our case, steps. So it's like GitHub Action. So it runs in Circle CI in our case, but it's just like a script that you run automatically on every commit, on every push.
And is Prometheus open source?
Yeah.
And Triton?
Triton, of course, yeah.
Okay,
all of this is of open source, in fact.
Okay, thank you.
Thank you very much. Do you have more questions? No? Ricard, thank you very much. It was beautiful.
Thanks.
Thank you.